Hello, friends.
Hello, Mr. Stone.
Hey, hey. What are the names of the poles of a magnet? So there's two kinds of poles, one on either end of your average magnet. What are the two poles called?
North and South.
North and south. So you have a north pole and a south pole. The north one is called the north pole of a magnet because it will, if you have the magnet free to turn, for example, it's hanging from a string or it's on a light floating platform, it'll actually turn until this north pole of this magnet is pointed in the direction we call north. That's why it's called the north pole of the magnet, because it points north if you have it free to move. The south pole is called that because it'll point toward the south if it is free to move. But in addition to their names, we know a little bit more about the magnetic poles. For example, if I put a south pole next to this south pole, what would happen? If you have two south pole ends of magnets near each other, what are your magnets going to do?
They'll repel.
Repel. So which poles attract? Opposite, as in a north near a south will be attractive. Which poles repel? The same. So this would be north and south. This would be north and north, or south and south. For number two, did you guys, when you were going through your study guide, those of you who went through your study guide, did you draw them or did you describe them with words? Because I could do either, whichever one is going to be more beneficial for you. I'm more of a visual guy. You might be different.
Yeah, I agree with Joel. I'd say draw it. It represents it better.
All right. Then I will go with what you guys said, and I'll draw it out. Around a bar magnet, which is what I've drawn here. This is a bar magnet. There's also like horseshoe magnets, like this. A horseshoe magnet is just a bar magnet that's been kind of bent in the middle. So its magnetic field actually kind of ends up looking like half of a bar magnet's. But anyway, that's not the question at hand. Around a bar magnet, the magnetic field, which is the lines that represent the force, arc around from one pole to the other. So they come from the north and they arc over to the south. And they spread out from it as you get toward the middle. So the arc gets taller at the middle and then kind of comes around. Now, it is important to remember that we have a convention about these lines. When we represent force as a line, we do it as an arrow to indicate the direction that the force pushes you at. As you see right here, the direction you'd get pushed in would depend on whether you were a magnetic north or a magnetic south. If you are a magnetic north, this thing's going to push you away. If you were a magnetic south, this one would push you away. So we have to pick one, and we'll just always draw it as though it is that one. So we always draw them as they would act on a magnetic north. So we would have it being pushed away by the north and pulled toward the south. So when we add arrowheads to all of those arced lines, they end up pointing from north to south. In your margins, if you have margins, I know most of you probably didn't print this, but rather did it on like loose leaf or whatever. But if you've got margins on your paper somewhere, either you printed mine or wrote your own, Remember that field force lines of magnetism are drawn from north to south. B and C, if we have two like poles, like let's say this is a north, and here is a north, what would these lines look like? Well, remember, we draw it as it would act on a north, so it can't go from north to north. Both of them would repel. If you were closer to this one, it would push you away, and then as you got close to this guy, he'd also be pushing you away. So you'd kind of have to arc away from both. And like kind of a reverse tug of war where everyone is pushing instead of pulling. If you were right in the middle, perfectly like not up or down, just beautifully centered between the two magnets, there'd be this point where everything kind of bounces out and you'd just be stuck there. Like a roller coaster that gets stuck at the bottom of a hill. Like it can't go up the wall, it can't go down the wall, it's just there. Of course, it would love to arc over to the other side. So you could draw it out. You could flesh this out a bit more, but the important thing is that your line's going to bend away. For two unlike poles, two opposite poles, so if this was a north and this was a south, in that case, of course, if you had the north here and you were kind of far away from the south, it could still arc around to the back. But what if it was right here? This south is a lot closer. It's going to attract you strongly. So between the two, you get this nice uniformity, except for if you're at the edges, it arcs a little bit. So it'll go between the two poles as opposed to away from both. If my drawings aren't satisfying for you, that is an illustration that is like a graphic on this study guide later on. Around a long, straight current carrying wire. All right, we actually have to draw that for number 4. So even though Joel and Kyle just asked to have these described by drawings, I'm going to write this one out in words because I'm going to draw it in a couple minutes anyway. Around a long, straight current carrying wire, the magnetic field around a long, straight current carrying wire is in the shape of concentric. That means all of the circles have the same center. Concentric, everyone has the same center. Circles around the wire. Around a loop of current carrying wire. That's a solenoid. It ends up actually kind of looking like a bar magnet, basically. If your current is going through this way, then you would use the right-hand rule all the way around. So it's going up through this loop. That means it arcs this way, north to south. So this, all of these end up pointing this way from every single loop. And then at the ends, it arcs around like a bar magnet. So it's like a bar magnet, but in the middle of that current carrying loop, you get this extremely concentrated, powerful field. And then finally, around the Earth, this is another one that looks suspiciously like a bar magnet. There's the Earth. Here's the geographic north. Here's the geographic south. Notice that I drew them tilted because we have seasons. But if the north pole of a magnet is attracted to the north pole of the Earth, what does that mean is true about the Earth's north pole? Well, what do you have to be to attract to the north end of a magnet? The only thing that is attractive to a magnetic north is a magnetic
south.
South. So geographic north is also magnetic south, which makes geographic south a magnetic north. So our field lines would be going from Antarctica to the Arctic. So from down here where there are penguins to up here where there are polar bears. It makes that bilobed shape that you expect from a magnetic field. So basically, it's like there is a gigantic bar magnet jammed inside of the Earth. Now, when the sun blows out solar wind, that does kind of change the shape of it, because that's like putting one magnet near another, right? They influence and kind of bend each other's lines, as you see for B and C. But if the sun is nice and calm, and our magnetic field being its own magnetic field is the only thing there, it looked like this. What is a magnetic domain made out of? Well, first of all, remember that a magnetic domain is how you get a permanent magnet, not an electromagnet. There is a difference. A permanent magnet doesn't need a battery. So magnetic domains are important for permanent magnets like refrigerator magnets, etc. But basically, the important thing to remember is that the source, and write this somewhere, the source of all magnetism is the motion of charge particles. So in the atom, you have the nucleus, which we can imagine as being stationary. Maybe it's not, but whatever. We got the nucleus. And what's doing most of the moving is the orbiting electron, a little negative particle that orbits the nucleus. So it's doing a lot more moving. It's kind of like the sun versus the Earth. The Earth is zooming around the sun, less so. But if this motion generates a magnetic field that is like this, well, most elements will tragically, it's not tragic at all, it's just chemistry, have the opposite thing happening too. If this one's going around this way, you might get another electron paired with it that goes around in the opposite direction. Going around in the opposite direction, it makes an oppositely oriented magnetic field, and they cancel. There's only 3 elements on the entire periodic table that don't do that. Or another way of saying that is there's only 3 elements where the structure of their electrons does not prevent them from being magnetic. Does anyone know what those three ferromagnetic elements are? The three that can form permanent magnets? If you can just give me one, I'll be happy. Oh, wait, hang on. We got it in the chat. Joel said iron. Can anyone give me another one?
Cobalt.
Iron, cobalt, and finally,
Nickel.
nickel. Iron, cobalt, and nickel are the three elements that don't cancel out in this manner. So if you have a piece of iron, does that automatically make it a magnet? And the answer to that is no. Because if you've got an atom of iron acting like a magnet, like this here, well, what if your neighbor is set up the opposite way? Well, it still cancels out. So you would need your neighbor to have the same orientation you do. And if you have a bunch of neighbors, then instead of canceling out, you add up. So you got a north over here that is 3 times as strong. You've got a south over here that's 3 times as strong. So a magnetic domain is a cluster of atoms with the spins of their electrons, that's what this stands for, E negative is electrons, aligned to reinforce their magnetic fields. So if you had a slab of iron, there might be a region over here where they're all lined up. Okay, so you've got a north here and a south here. And then that might make that there's a south here and a north here. Well, those aren't very well lined up. And then here versus here versus here. And they're random, right? If they're random, then they're not really working together. This is unmagnetized. There are domains, but the domains cancel out. For it to be magnetized, you want this to be all one big, well-aligned domain. And all of the ways of making something stop being a magnet involve breaking up those domains. You can either heat a magnet so that the atoms shake themselves out of alignment, or you can beat a magnet and knock them out of alignment via force, like hitting it with a hammer, dropping it on the floor, or whatever. Or if it's magnetized one way and you want it to be magnetized a different way, you can put it near another magnet that's stronger, and that magnetic force will turn these into alignment with it. So improperly storing a magnet near other magnets can make it less powerful. Give me 1 second. I need to close out a window. There we go. Number 4. This is the one I mentioned a moment ago. We got to draw the magnetic field around each wire. Get your right hand primed because these involve the right hand rule. Remember that in the right hand rule, your thumb represents a current carrying wire and it points in the direction of the current. So here is here's the positive terminal of your battery, here's the negative terminal of the battery, and the current goes that way. Your fingers represent those concentric circles around the wire of magnetic field. So if your thumb points this way and your fingers curl around like that, your circle goes north to south in this direction. So the north would be at your knuckles, the south would be like over here on the other side of your palm, and it's going from north to south. curling in that direction. So in this one, we point our thumb down to go along with the current, which is going down the plane of the page. And my fingers would curl into the page on the left side and then out of the page on the right. So over here, into the page. Into the page, you draw circles with little X's. Hopefully you remember that from like the fletching of an arrow. If not, go back and watch my older lectures. And then over here, they're going to curl back up. And here are the points of the arrows coming up. And remember that these are concentric circles. So it's going to kind of loop over like this. If you drew it a bit more simply, I kind of wouldn't blame you. Like if you just drew it like that, that works too. I just wanted to make sure that before the test, you guys haven't forgotten the into and out of the page symbols. Those are important. For the other one, we need to point our thumb in the opposite direction because in this one, the current is going up the page. So point your thumb up the face of the page and notice that your fingers curl. On the left side of it, it's coming out of the page. On the right side, it would be going back into the page. So our circles would be looping over in kind of that direction. Wow, that one looked really good. That's probably one of my better magnetic field drawings in a while. But you'll notice that changing the direction of the current reverses the direction of the magnetic field. This is super important because there's a ton of stuff that works like this. Have any of you ever used an electric drill? Like maybe you had to hang a photo or something on the wall and you used a drill to, put a screw into the wall.
Yeah.
Yeah, or maybe you had to drill a hole into a block of wood. I know anyone who's in based club, that's
we are good at drilling.
Yeah, you guys just drill holes all the time. But if you're drilling something, most electric drills have a button on there that can make it turn the other way. So you can, if you're using a drill as a screwdriver, you could screw in and then hit the reverse button. And then when you pull the trigger, it'll unscrew it. Well, how is that accomplished? It's a switch that connects it to the battery backwards. So here's your positive and negative, flip that, and your magnetic field reverses. Since that motor works by this magnetic field, if this reverses, it'll spin backwards. So reversing the current reverses the magnetic field. You can reverse the direction of the work done by the magnetic field. So you can make your motor spin backwards. Or if you had like a fan, I realize that we live in Florida where you don't have seasons, but for anyone who has lived anywhere else or has family that you visit during the summer to try and escape the heat, ceiling fans have a switch on them that at the change of seasons, like from winter to summer, you're supposed to flip that switch. In the summer, you've got hot air that you want to force down so that you can get some circulation. So you want it to blow in that direction. In the winter, you're going to want to circulate that air kind of up the walls as opposed to forcing it down. So you flip the switch and the blades spin in the other direction to drag the air in the other direction. Again, accomplished by reversing current. All right. Page 2. We're making progress. This one's easy. Draw field lines to represent the magnetic field around a bar magnet. It's just arcing lines of field force that get farther away from the magnet at the middle. Remember that they go from north to south. And as you get farther away from the magnet, they should spread out a bit more. So the poles, you should have your arrows be really, really crowded to indicate that the magnetic field is really strong there. And as you get to the middle of it, they should be spread out to indicate that the magnetic field is weaker there. The concentration of these field lines is a quality or quantity called magnetic flux. Where you have a lot of field lines passing through, that is an area of high flux. If you have only a few or they're spread out, then that is low flux. So this area has a lower flux than near the pole. So flux is kind of like a measure of how densely packed these lines are, or how many lines there are. It's more the count. And then if you had like a 1 meter by 1 meter square, where you have a lot of flux per square meter, that is a Tesla. Like that's the definition. So you have more Tesla of flux density or magnetic field strength, if you want to think of it that way. But here where the lines are all packed together in this box, that measurement, this is more Tesla of flux density than you have here in the middle. So if you were struggling to really understand what a Tesla is as a measurement, when you're drawing this, as you see here, they're more spread out. Here, they're more concentrated. That's a representation. When you draw that square, the count of magnetic field lines per square is a visual way of representing what a Tesla measures. Now you'll notice that this goes out of the north and to the south. But you can also draw a magnetic field by taking a sack of compasses and dumping it around a bar magnet. Remember that the pointy end of a compass is the north end. So you put a compass near this north, it's going to repel it. So the point would point away from this north. It would point toward a south, which is why a compass works in the first place. But here, what would it be doing? Well, it would start to get attracted to the south, but pushed away from this north, so it'd kind of be angled like that. And then here in the middle, if you put the compass here, the north pushes this, the point this way, and the south draws that this way. Down here, it'd start to point down toward the south, but there'd still be a little bit of repulsion from the north, so that'd keep it from going like straight down to it. And hey, those compasses are drawing, if you connect those dots, you get the magnetic field lines we drew over here. So if you have a question with like a bunch of blank compasses around a bar magnet, just draw the magnetic field around the bar magnet and you're good. The compasses will show you the magnetic field lines, kind of like the iron filings in our gizmo. But that's the secret to that. If you have a compass or magnetic field one, you can draw it out. How can current be produced in a loop of wire? And what is the direction of the current that you make? Well, if I have a loop of wire, like a solenoid, and I just connect it to an ammeter. And that's all there is, just a wire attached to a current reader, no battery involved, no magnets involved, nothing. It's going to say 0 amps of current. Well, it's just a wire. A wire doesn't have a current in it just because it exists and has been bent. But what is something I could do to put a current through that? Of course, I could put it in I could attach it to a battery, or I could put the ends in a socket or something. But that's not induction. Induction means that you are using your own influence to force something to happen. Electromagnetic induction, how can you produce a current? Well, you can take a magnet and stab it through that loop of wire. As that magnet moves through the loop of wire, a changing magnetic field, this is what Michael Faraday discovered, a changing magnetic field produces a current in a nearby conductor. So as long as this magnet is moving, motion is a kind of change. And it changes its magnetic field as it moves. So you're going to have, let's say, 2 amps of current read as long as this is moving. As soon as it stops moving, it stops changing, and we're going to go back to 0 amps. So if you just put the magnet in there and left it, it's just sitting still, no current. But if you move it, you drop it, you wiggle it, you stab it through and pull it back out, as long as it's doing something to change, you'll get an induced current. So how can a current be produced in a loop of wire? A current is induced in a loop of wire when a neighboring magnetic field changes. As soon as it stops changing, the current goes away. Why? Because the natural state of a wire is to not be carrying a current. You can tell that is the truth because resistance exists. If a wire was cooperative, then it would have no resistance. But there's another layer to that was discovered by Lenz. Lenz's law tells us that even when it does carry a current, it fights back. The direction of the current will make a magnetic field to oppose the change in magnetic field that induced the current in the first place. I've said it before, I'll say it again. Think of Frankenstein's monster. For those of you who read the book, what is the Frankenstein monster's #1 goal in existence? To kill his creator. He followed him all the way to the Arctic or the Antarctic, one of the cold places on the planet, hoping to kill the guy. And then the guy dies on the boat, and he's heartbroken that he doesn't get to kill him himself. So just like Frankenstein's monster, it wants to destroy the thing that created it. Lenz's law, the Frankenstein monster of magnets, is that the direction of the current will make a magnetic field that fights back against the change in the magnetic field that causes it to exist in the first place. So if this magnet has a north here and it's falling through this loop and that creates this current will go in a direction to have, I guess it'd be this way maybe, but whatever produces a north here and a south here. Why? Because this north will repel that, and that'll try to slow it down from falling. It's falling through the loop. That's what creates the current. So what happens? It fights back against the action of it falling. So Lenz's law tells us that the direction of the current will be such that its magnetic field opposes the change that induced it. This is what's also called magnetic braking. That's how the brakes on Shikra at Busch Gardens work. Label the magnetic poles shown below. Well, we have a pole here, and the lines are pointing away from it and toward this. So what does that make this blank pole here? The lines are coming out from it and directed away from it. You got a 50-50 shot. There's only two kinds of poles, guys. This one right here.
Well, they're repelling each other, so would that be a north?
This is a north. You can tell because the lines are pointed away from it. And as you said, it repels this guy, so this one is also a north. And you can tell because the lines are pointed away from it. That makes this a south and this a south because you can't have a north without a south. They're always paired up. All right, now let's look over here. These lines look different. It's going from this one to this one. Even though they're on different magnets, they still have motion like toward. So these are not repelling, these are attracting. We know these are going to have to be opposites, but which one is which? This one has the lines coming out of it, and they're heading toward this one. Well, magnetic field lines always go from north to south. And then you just fill in the opposites on the other sides. Whoa. What happens to the poles of a magnet when it's broken in half? Well, I just spoiled that a second ago. When a magnet's broken in half, does that isolate the north and the south, and now you have a piece that's just a north? No. The domain is still there on the atomic level, and even on the atomic level, if you have a north, you have a south. So each half of the magnet will have both a north and a south pole on it. So if we have a magnet like this, cut it in half so that we have this half here and this half here. We would have a south on this end because that was the southern direction of this magnet. We'd have a north here. And in fact, our pieces would actually pull together. Like their inclination would be to rejoin, unless you turned one of them. Number 9. Shown below is a loop of wire with a current running in the direction of the arrow. Label the magnetic field both inside and outside of the loop. You got your right hands ready? So we're going to use the right hand rule. The current's going this way, so at this bottom straightaway, we know the magnetic field is going to be looping over like this. And then from here, it's going to be looping over like this. And you can just go ahead and trace that all the way around. And just to be sure, oh yeah, it does still work. So if it's going from north to south, then the outside of it has got to be a north and the inside of it is going to be a south. Because it says to label the magnetic field both inside and outside of the loop. Easy peasy. Just use the right hand rule whenever you have a current carrying wire and it'll always work out for you. We're on the last page. We're almost done. Number 10, boils and ghouls. What is mu naught? Well, I can tell you what it's worth. Mu is a lowercase Greek letter. Oh, there's a capital mu as well, but this is lowercase mu. And naught is subscript 0. So what is mu naught? It's mu sub 0. And that is equal to 4 pi times 10 to the negative 7th power Teslas times meters divided by amperes. All right, so that's the value of mu naught, at least the numerical value of mu naught. But what is it and why is it important? Well, mu naught is what we call the permeability. Now, permeate means to spread through. Like if you fart in a hot car, the smell will permeate throughout the car. Or I guess the same thing works with Febreze, but for some reason kids think farts are funny, so maybe that made you pay attention. Or if you paid attention in biology class, cell membranes can be permeated. If you have water on one side, it'll permeate through to the other side of the cell membrane. It'll move throughout. Permeability means to move throughout. So it is the permeability of space. Now, I don't mean space like outer space. I mean like distance in this universe. There is space between my face and this microphone. Could I have a magnet there? Sure, why not? There's a magnet in the microphone. I know that much. So let's say that magnet is reaching out toward my teeth. That space has to let the magnetism move through it. If the space is cooperative, if it lets it move through easily, then it's highly permeable. If it fights back and it's hard for magnetic fields to move through space, then it has poor permeability. So what the permeability of free space is a measure of how well magnetic force moves through distance or space in our universe. Why is it important for our work with magnetism? Because it is the limiting factor for how well a magnet can work in this universe. If we had a universe with extremely low permeability of free space, then we would have most of our magnets would not work very well at all unless you were right up on them. So it's a limiting factor for how well a magnet can work at a distance. If you're extremely cynical, then it's a constant that you have to plug in. And it's a constant of proportionality that you're always going to have to put into our magnet problems. Why is it? Because it tells you something about how our universe lets magnetism move through it. Let's practice using it for 11 and 12. If you have not yet done so, now would be a good time to grab your calculator, although if you're slick, you can do number 11 without a calculator. A long, straight current-carrying wire has a current of 4 amperes. You place a magnetometer near it and measure a magnetic field, B, of half a Tesla. How far away from the wire did you place the magnetometer? All right. We also need mu naught, but I've already written that. The equation to figure out the magnetic field around a long, straight current-carrying wire is magnetic field measured in Tesla is equal to current measured in amperes times mu naught divided by 2 pi radial distance from the wire, which is what we want to know. We want to know the distance from the wire. So plug in and we'll figure it out. Our magnetic field is half a Tesla. That is equal to 4 amps times 4 pi times 10 to the negative 7 Tesla meters per amp divided by 2 pi radius, which is what we want to know. Let's get rid of common terms. We have a pi on the top and a pi on the bottom. That goes away. We have a Tesla on this side and a Tesla on the opposite side. We have amperes per ampere, that cancels. So we're left with the only unit being meters, which is good because we want to find a distance. Distance is measured in meters. We're trying to solve for 2r. So we need to move 2r to the other side. 2r times 1/2. Well, what's 1/2 times 2? Oh, come on, that was a slow pitch. What's 1/2 times 2? You can hit the space bar to unmute yourself. 1/2 times 2. Come on, I thought this was...
I don't know why no one's talking, but it's 1.
It's 1. So 1/2 times 2r is just r. So r equals, and we've gotten rid of this 2 and the half now. 4 times 4 is 16.
I'm sorry, I was using my phone as a calculator.
2 times 1/2, you needed a calculator, my man.
No, the calculator was up, and I'm also doing another thing for my math class, so I need the calculator up still. So I was hoping someone else would answer.
All right, so Andy was multitasking. That's his excuse, and I think somebody responded in the chat. All right, Joel responded in the chat. So to put this in a proper scientific notation, we're going to move the decimal. So 16 times 10 to the negative 7, move it over 1, 1.6 times 10 to the negative 6 meters. So you put it pretty close to the wire. But yeah, no calculator needed for that one. I guess you could have just plugged it into a calculator. You'd gotten the same thing. Next one. All right. So Joel has been really excited about this unit. He's really excited about magnets. And the other day, he spent his whole afternoon, he got like a little wooden rod. He found it in the garage or the shed or whatever. Well, 10-centimeter long wooden rod. And he took some copper wire and he just started winding it around. He's like, I'm gonna make a magnet, it's gonna be awesome. 5,000 loops, took him all day. So we have a solenoid, a coil, that is 10 centimeters long. I prefer to think of 10 centimeters as 1/10 of a meter. You can call it 10 centimeters if you want. And the number of loops on it is 5,000. No unit for that, like it's a counting number. You attach the wire ends to a battery. So Joel takes a battery, puts it to the two ends of the wire hanging off of his coil, and we get a current of 6.28 amps going through it. What's the magnetic field in the middle of it where the rod is located? So if we replace the rod with a magnetometer, what would it read? The formula to find the magnetic field for a solenoid is probably easier. It's just current mu naught again. And then the number of loops makes it stronger. But if they're far apart, because it's a long coil, that makes it weaker. So you have the coil density. Loops per meter, basically. All right. So we're just going to solve for B. So this is going to be kind of easy. 6.28 amps for pi times 10 to the negative 7 Tesla meters per amp times 5,000 divided by 0.1 meters. You can go ahead and feel free to put that into your calculator as is, because we've already got it set up to solve for B. So 6.28 times 4 times pi times 10 to the negative 7 times 5,000 divided by 0.1. And we get a magnetic field of 0.395 Tesla. Easy stuff. Explain Lenz's law. We already talked about Lenz's law. That is that the current induced will make a magnetic field that opposes the change that induced it. So when electromagnetic induction occurs, the current in the wire will produce a magnetic field that opposes the change that induced the current. In the video where I introduced this concept to you, I showed a copper pipe and a powerful magnet being dropped into it. Now, we all know and love the fact that if something is falling on this planet, it's going to accelerate downward, picking up about 10 meters per second of speed every second it falls. 9.8 meters per second. We all know that. Hopefully. But that magnet didn't do that. It fell slow. If you think back to free body diagrams, if something is not accelerating due to gravity at 9.8 meters per second squared, then there has to be a lower downward net force. There has to be some sort of upward force kind of hitting the brakes, slowing it down, reducing 9.8 to, I don't know, like 1 meter per second squared downward. Well, what was the upward force? Magnetic repulsion. As that magnet falls down the copper pipe, it induces a current in the copper pipe. You know, simple Faraday stuff. Changing magnet gives you a current. But that current is going up the pipe, so its magnetic field is in a direction that repels the magnet as it falls. So the magnet gets slowed down. It opposes the falling action that caused the current to exist in the first place. This, again, is magnetic braking. It's how Sheikah's brakes work at Busch Gardens, which is nice because you don't have to replace brake pads as often. Instead of friction against a rubbing, sticky surface, you just use electricity to do the same thing. It might generate heat, though, so you got to be careful about that. But it might also generate some electricity you can use. Maybe lower the park's power bill. Also, this magnetic braking is used in electric and hybrid cars to help recharge the battery. When you hit the brakes, this Lenz's law thing can be used to generate a little bit of current so that the battery recharges a bit every time you're hitting the brakes. That also helps save wear and tear on the brake pads. It's cool stuff. This Lenz's law thing is very useful. I just described some examples. If you want to draw it, that's up to you. I already drew it a couple pages ago. Describe all the methods of inducing voltage in a loop of wire. We keep saying induce a current, induce a current, induce a current. You can't have a current without a voltage to push it. So really, this is how are you able to induce a current, induce a voltage in a wire? Well, number one, you can move a magnet near the loop of wire. Or if you think relatively, flip that on its head. You can move the magnet near the loop, or you can think relative. All right, we got a response in the chat. Let me see. I am bad at using my mouse with this weird claw grip. Move the loop near the magnet. Joel is completely correct. So move the loop near the magnet. Either way, the magnetic field's effect on the loop will have been changed by relative motion. Or the third method, which has way more to do with transformers, turn a nearby electromagnet on and off near the loop. So that wound up wire that Joel spent all afternoon winding up on the rod, if you put it to the battery, it gives you a magnetic field, a compass jumps toward it. But then, If you disconnect it from the battery, the magnetic field goes away. Existing to not existing is a change, and a changing magnetic field will induce a current. So if Joel tried to practice his Morse code by tapping the wire onto the battery, making and breaking connections, he would be able to induce a current in a nearby loop by that method. And in fact, that is how transformers, not robots in disguise, but rather transformers as in things that you plug into the wall so that you don't blow up your phone, that's how those work. You have a coil that goes into the wall. The wall has 120 volts, but it's alternating current. Alternating current means that it's going this way, now it's going that way. It's going this way, and now it's going that way. It's going this way, and now it's going that way. Back, forth, back, forth. That is a change. Changes induce current. So the neighboring coil gets a current induced in it. If there's a different number of loops, it's a different amount of current. So how do transformers change voltages? By this principle. And if the primary, that is the input coil, and secondary, that is the output coil, this one, have different in number of loops or length, as in this equation here, those two, number of loops or length of the coil, the output induced voltage will be different, aka it will be transformed into something else. So if we have 120 volts here, and this has 1/10 the loop density, then it would have 1/10 the voltage. And of course, it'd be direct current. This is an example of what is called a step-down transformer, where you have fewer loops in the output coil, so the voltage is reduced. It steps down to a lower value. So in a step-down transformer, you have fewer loops or less loop density in the output coil, and the output induced voltage is reduced. In a step-up transformer, you have more loop density in output coil, so it has a higher output voltage. And then how are the voltage and current related in transformers? That actually goes right back to our old unit that we had the last 9 weeks. Power is current times voltage. Power is energy over time. Energy is a conserved quantity. It can't be created or destroyed. So whatever energy you put in, you got to get out. So the power must remain constant. If your voltage goes up, your current has to go down. So they are inversely related. How are they voltage and current related? They're inversely related in a transformer. This is how you keep power lines from melting. They have a ton of energy. So how do you prevent them from like overheating from the resistance and melting down? We use step-up transformers. Transformers are mounted on the power line poles, and the transformers are step-up. So you get a huge voltage, which gives you a low current. The low current experiences very little loss of energy to heat from resistance, so that your power lines don't melt. If you had a low voltage with a high current, then your power lines are going to melt down. Not good. And with that, we've gone over the whole study guide. Any questions, any concerns, any comments, hopes, fears, dreams you want to share?
I think we're good, Chief.
All right. Well, in that case, don't forget that there is a gizmo due Friday at midnight. It's reasonably easy. It's energy conversions. Just remember that everything will, stay the same in amount because energy is conserved, like we were just talking about. With that, I'm going to let you guys go. Adios. Good luck on the upcoming test, and I will talk to you shortly.
Peace.
Later.